Hey there, welcome to this explainer. Okay, we're just going to dive right in. Today, we're taking a pretty fascinating journey through a world that is literally all around us, but mostly invisible. We're talking about the science of pressure calibration. We're going to move from some incredibly daring 17th century physics experiments at the tops of mountains, all the way to the super precise mathematical standards that keep our modern industries safe today. So if you've ever wondered how we actually know a pressure gauge is telling the truth, well, you are definitely in the right place.
Here is our roadmap for this explainer. We'll kick things off with the history of how pressure was actually discovered, hit on some key pressure types and definitions, and then look at the physical calibration equipment. After that, we'll get into the strict modern calibration methods, and finally, we'll wrap up with the math behind calculating measurement uncertainty.
All right, part one, the history of pressure, its discovery and its origins. Before we can even think about calibrating a measurement, we have to understand what it is we're actually measuring, right? And for a really long time, humanity didn't even realize that the invisible air around us actually had weight.
The big breakthrough? That happened back in 1644. An Italian physicist named Evangelista Torricelli filled a 1-meter glass tube with mercury and basically flipped it upside down into a basin. The mercury dropped, left a vacuum at the top, and settled at exactly 760 millimeters. Torricelli figured out that some invisible force on the Earth's surface was pushing down on the basin, holding that mercury up. It's kind of like a giant invisible hand. Well, just 4 years later, in 1648, the brilliant French thinker Blaise Pascal caught wind of this. He reasoned, hey, if the weight of the air is pushing the mercury up, there should be less air pushing down if you go higher up. So he actually sent a team to climb the Puy de Dôme mountain in France to test this out, which, by the way, meant hiking up a literal mountain with a giant, fragile tube of incredibly toxic mercury. But man, the effort paid off. Sure enough, the mercury level dropped as they climbed. Pascal absolutely proved that air has weight, and he coined the term we still use today for this force acting evenly in all directions: pressure.
Moving on to Section 2, Pressure Types and Key Definitions. Now that we know where the whole concept came from, let's lay down the foundational vocabulary we need before we can start measuring anything in a modern lab.
At its absolute core, pressure is simply defined as the perpendicular force applied per unit area. Or if you're dealing with a closed container, it's the tension at any point in a fluid. So the basic equation is P equals F over A, force divided by area. Pretty straightforward. And in a nice little nod to our mountain climbing physicist, the Standard International System of Units, the SI unit for pressure, is the Pascal. Now, you might be wondering how we actually define our 0 point when we measure that force. Well, absolute pressure starts at a true absolute vacuum, meaning literally 0 molecules, 0 pressure. But in the real world of industrial applications, we mostly care about gauge pressure, which is also known as relative pressure. Gauge pressure completely ignores the heavy blanket of the Earth's atmosphere that we're living in. It treats the local atmospheric pressure, which, remember, Torricelli found to be roughly 1,013 millibars at sea level, as its 0 point. So the really crucial takeaway here is that if your industrial gauge reads 1 bar, you actually have to add the local atmospheric pressure to that number to find the true absolute pressure.
Okay, Section 3. Calibration equipment, the tools of the trade. Let's move from those abstract definitions and look at the actual physical tools that make precision measurement and, more importantly, precision calibration a reality today.
Nowadays, we have these highly advanced digital calibrators. They use complex electronics and super precise internal sensors to generate and measure pressure. But honestly, the pure physics of it really shines in a traditional dead-weight piston manometer. This device is the crucial bridge between theoretical pressure and practical calibration. It literally uses known physical weights, physically pushing down on a piston that has a known surface area, to generate an exact pressure. Again, force divided by area. It's essentially Torricelli and Pascal's discoveries engineered into a perfect physical reference standard.
Which brings us to Section 4, Modern Calibration Methods. Having the right equipment is really only half the battle. To guarantee safety across global industries, metrologists need some incredibly strict rules. And those calibration rules have definitely evolved over the years. Initially, labs relied heavily on the older EN 837-1 standard. Then, by the 2000s, the German DKD-R 6.1 guideline emerged, and that provided a much more robust framework for testing. But today, the modern gold standard used by national metrology institutes is Euramet CG17. This is a highly detailed set of guidelines that dictates exactly how a pressure gauge has to be tested to prove its accuracy without a shadow of a doubt.
Euramet CG17 categorizes calibrations into methods A, B, and C, and this is entirely based on the targeted measurement uncertainty. And you can really see how the strictness scales up. If you want an ultra-precise method A calibration, where you're looking for an uncertainty of less than 0.1%, you have to test 9 different points on the gauge scale, perform 2 full upward and downward cycles, apply 3 preloads just to exercise the gauge, and then wait at least 30 seconds at each point for the pressure to fully stabilize. It is incredibly rigorous.
And that rigor, it doesn't stop at the procedure itself. It extends right into the environment. Because things like the density of air and the expansion of metals can actually skew the readings, Euramet CG17 demands rigid lab conditions. The room has to be kept between 18 and 28 degrees Celsius, with a temperature stability of plus or minus 1 Kelvin. Furthermore, the lab has to record the exact atmospheric pressure and the relative humidity during the test. Literally every microscopic variable is locked down and controlled. All right, Section 5. Measurement uncertainty and calculating errors. We've set the stage, we've controlled the environment, we've run the test. Now we arrive at the most complex but absolutely vital part of this explainer, the rigorous math required to actually prove a device's accuracy. Before you even touch the calculator, Euramet CG17 dictates a really crucial rule of thumb. The measurement uncertainty of your laboratory reference device must be at least 2 times better than the uncertainty you are trying to assign to the device you're testing. Interestingly enough, the older EN 837-1 standard used to demand it be 4 times better, but the modern Euramet standard settled on a strict 2 times ratio, which is enough to ensure total mathematical confidence.
You can kind of frame this whole mathematical process like a lie detector test for industrial gauges. The Euramet standard forces laboratories to check 3 main vulnerabilities. First, they determine the zero error. Basically, does the needle actually return to absolute zero when there's zero pressure? Second, they calculate repeatability by running the pressure up and down the scale over multiple cycles. So if I apply 50 bars of pressure 3 different times, does the gauge give me the exact same reading every single time? And finally, they check for hysteresis. This is the physical lag in the gauge's internal metals when dropping from a really high pressure back down to a lower one.
All of this comes together in an uncertainty budget calculation. You absolutely don't need to memorize the formulas here, but just think about the factors involved. You've got the resolution of the gauge, the standard uncertainty of your reference device, the zero error, repeatability, and hysteresis. The laboratory takes the standard deviation of all these separate variables, applies a rectangular or normal probability distribution, and then merges them all together, usually using a root-sum square calculation, to find the true, undeniable margin of error for that specific gauge. It's the whole shebang.
When you actually run the numbers, you get real-world readings. Laboratories track the applied reference pressure, and then they log the actual readings taken from the test gauge as the pressure goes up and then comes back down. Using those formulas we just talked about, the lab calculates the deviation and applies an expanded uncertainty value. That final value proves exactly how far off the gauge might be at any given point on its dial. It's just incredibly precise.
Which brings us to the ultimate so what. We've gone from Pascal climbing a mountain to complex standard deviation tables. But what happens to our modern world if a laboratory gets this wrong? Think about it. What happens if we miscalculate the uncertainty of a single industrial pressure gauge? From the fuel lines in commercial airplanes to the containment vessels in nuclear power plants, this microscopic mathematical precision is literally the invisible shield guarding our macroscopic industrial safety. Without calibration metrology, the modern world simply could not function safely. So the next time you see a pressure gauge, what will you see? Just a needle on a dial? Or centuries of physics and math keeping us all safe? I hope this explainer gave you a whole new appreciation for the heavy science behind the invisible weight of pressure. Keep learning and stay curious.